Now mine is working. So no need to worry about it.
Share my works. This work is based on this paper with Jala and Lady and stuff. So let me first by introducing our motivation. Of course, I think one of the most fascinating result in theoretical physics is the black hole entropy, because it depends on the speed constant, the speed of light, Newton constant, the Planck constant. So that means that it is a quantum effect because there's a quantum constant and gravity, and also the quantum gravity effect, and there's the gravity constant. So to understand how this entropy arises microscopically is the work of it's the spirit of understanding at least what is the quantum gravity theory is like. And the first success was achieved by Asherson, of course, and also Andrew Strominger and Waffas work in 1996. He understands some kind of a asymptotically flat black hole. And then it was later realized that's just a very toy model, or at least it gives us some motivation to propose this ADS CFT correspondence. It was later realized this can be understood in terms of ADS3 CFT2 correspondence. But in terms of ADS3 CFT2 correspondence, the story is much simpler and general, because it turns out we only need some kind of modularity relations of the two-dimensional CFT to understand or to reproduce this black hole entropy from the microscopic states counting. So the motivation of this work and a lot of related works in the past several years was how can we generalize the modularity relation from the CFT to higher dimensional ADS CFT. So what is the modularity in lower dimensional CFT? Is, for example, the first very famous formula of CFT2 is known as the Carney formula. That means the entropy, or for example, the entropy is the log of the degeneracy of the state, and the entropy is given by CFT data by central charge and also the conformal dimension. And this structure is telling you have left movers and right movers. In order to reproduce that, what usually people do is to say, let's start from partition function, which is defined neatly by this definition, the trace is over all of the states. And this partition function satisfies some kind of SL2C modularity, and it's actually some kind of symmetry. If I just define a Z0, which is up to a phase equals to this partition function, and then Z0 tau equals Z0 minus 1 or tau, this is a symmetry of the partition function. And this symmetry, modular symmetry, comes from the fact two-dimensional CFT, and CFT is something describing the shape. It doesn't care about how far away between 2 points, but it is a shape preserved transformation. So the physical theory defines on such a manifold will depends on the shape of the manifold. And in two-dimensional torus, the shape is described by ratio of the two circles, one contractible circle and one non-contractible circle, which are called A and B. So tau is the ratio between the lengths of two circles. So if you define the tau to be B over A, that may be tau, and the minus 1 over tau is the A over B minus. And then these two parameters just define the same shape. So physical theory define only should have the same partition function. That's just a simple. And that's the origin or geometric origin of this modularity relation. And just by this simple relation that you can extract the asymptotics of the partition function to be is pure phase times 1, and 1 just come from the identity operator. And that makes it easy to evaluate the degeneracy or prove the Carney formula, which is just to say in order to compute the degeneracy we just need to do an inverse Laurent transformation of the partition function, and then that's this one. And when you approximate this partition function to be 1, and then you can evaluate its integration by saddle point approximation. And that's just simply give you the Cardi formula if you compute the saddle point value of the tau to be this one. So Cardi formula is very easy to derive in two-dimensional CFT. And the lesson we learned from this example is, in order to extract the high temperature behavior of the CFT, we only need the 2 universal features. One is there's a Casimir energy, we need to compute it. That's very important. And the dominant term contributing to the partition function in the dual channel under the modular transformation is just an identity. There's an identity operator. And this seems to be very general. All of the CFT seems to have an identity operator. And so that means modular just originates from some kind of a conformal symmetry, because our partition function should only depend on the shape of the manifold where this theory lives in. So, question is, how can we generalize this to higher dimensions? And because in higher dimensional manifolds, we will definitely have more structures. How can we do that?
Sorry, I have a very stupid question. So is it possible to perform the integral without doing saddle point?
So in general, let's say, then you need to specify what this z is. Let's say
it's just a 1.
if it is just 1, then this integration is some kind of a saddle function. So it is.
Is that result meaningful?
So it's like doing. So this is a saddle, and then the higher order, the other correction just focus on Gaussian contribution of the near the saddles. So it's a higher order corrections like giving you the other contributions. You can count that order by order. Yeah.
So I have even more naive question. So in the Cardi formula, so is S a number or operator?
S is a number. S is entropy.
Yeah, but how to interpret L and L0 bar? Are these operators or numbers?
It's an operator. The conformal dimension of the operator is a number.
So I know how this acts on the vacuum, but you're saying that this can be defined for any module.
So
that's the point.
Just for specify. So given a black hole, so it contains the mass and angular momentum, and the black hole mass is the L0 plus L0 bar. Black hole angular momentum is the L0 minus L0 bar.
I see.
Roughly. Yeah. But just for example, if you by Bacon-Hawkins-Stein entropy formula, S just equals to area over something, and the area in BTZ black hole is just proportional to the horizon size with the power, and that can be written as the black hole mass and angular momentum. And ADS safety corresponds is telling you mass plus angular momentum is L0. Okay, so what the example we want to study is the ADS5 CFT4. So on gravitational side, we of course want to study what is ADS5 black hole first and calculate its entropy. This is already very difficult task. For ADS5 process 5, there are 2 angular momentum and 3 R charges. And 2 angular momentum here and 3 R charges are just the Cartan generators of S5. And to find ADS5 black hole solution, I think the project starts in 20 years ago, 2004, and it was finally accomplished in 2011. First, this is one of the paper in 2005 by Professor Yu Hong and other Christoph Pohl. And they found some non-supersymmetrical solution, but some of the equal charges and angular momentum. I just copied a paragraph from their paper. You can see this is a very difficult task. They say they find the solution by guesswork and conjecture. I don't know how they guessed. And then finally, they use mathematical check. Okay, this is the right solution. This is not easy. At least I cannot do that. And then, but there are some simpler cases like the BPS solution, with all the charges are not equal. And this solution was found by some very nice complex geometry method, I think, and found in 2006. And 5 years later, Shuangqing Wu in Xinhua Normal University find the most general ADS5 black hole. And this solution occupies at least 3 A4 pages, even if it's an analytic solution. So it's the purely picture is not very intuitive to but I just show you what this solution is like, much simpler and half A4 pages. That's the ADS5 part. So you can see there are 3 3 U1 charges or U1 gauge fields that corresponds to the Cartan directions of SO6 or S5. And there is the angular parts, and this is some kind of calorimetric. So this is the exact solution. With the exact solution, the good thing is you can compute its entropy. And entropy is actually very simple.
The previous page, does it include the
No, there's no S5.
compact horizon or non-compact?
Compact. It's
only compact.
Only compact. This is the horizon is S3. And for non-compact horizon, I think that's another story. I think some people are still looking for most general solutions. So because you have a black hole, that's a geometry, then you can compute its horizon area, and that gives you black hole entropy. And the black hole entropy is very simple. Can be written in terms of the charges and angular momentum. So this formula backs explanation microscopically if there is such a simple formula. And also, these charges and angular momentum satisfy these nonlinear constraints. And why we have these 2 formulas, we want to understand it from the dual and force Young-Mills theory and use force Young-Mills computation. So in 2005, even before discovering this black hole, Maldacena, Minwala tried to study a superconformal index of N4 super Young-Mills. Try to find whether any ADS5 black hole entropy can be understood in terms of a superconformal index. And unfortunately, they failed. And they find the partition function at the large n order is of order n0 or of order 1. Not of order n squared, like what the black hole entropy would require. So this mismatch was believed due to the cancellation between the bosonic and the fermionic freedom. So, and it takes 12 years for people to realize, okay, let's take a step back. If you are able to find the leading order of a partition function to be of this form, let's say you have 3 chemical potentials correspond to 3 different U1 gauge fields, and the 2 angular velocity correspond to 2 angular momentum. If you are able to find the leading order of a partition function at the large n limit, is this one. And there is a mysterious chemical potential constraints, they must add up to be 1. Then Zaffaroni in 2017 say, you just do this functional analysis, just do extremization of this entropy functional by saddle point, and you will be able to reproduce this entropy. So, and then this is discovered in 2017, and then the question becomes, how can we reproduce this partition function and together with these constraints from the N4 super Young-Mills computation by computing the superconformal index? And compared to what Maldacena and Minwala did in 2005, the progress made was people realized that this chemical potential constraint that was telling you chemical potentials for black hole must be complex. And the leading order of this one seems to be very similar to the known supersymmetrical Casimir energy. But it's not identically supersymmetrical Casimir energy because that kind of terminology was defined find for chemical potentials not equals to 1, but linear combination to be 0 instead of 1. So how this 1 arises was the question starting from 2017. And then to understand this chemical
So just to make sure, so in that log Z, you include the cosmic energy or not?
this is just the cosmic energy.
No, but first you have a cosmic energy times the index.
I should say, oh, okay. So this log Z is just the index by definition. It's just the trace over -1 to the f, p to the whatever.
But for some reason, the formula coincides with cosmic energy.
Yes. And so if you just take a large n limit in the leading order, we'll do that.
What you're saying is that the difference is the constraint.
Yes. If you evaluate these constraints, let's say this is not equals to 1. Let's say it is, let's call it x. Then, by using saddle point approximation, this is just pi. You can see all of these terms will gone because they are homogeneous. Okay, they're just the order 1 term in chemical potential. So all of these terms will cancel. So the only term surviving to contribute to the entropy is a pi I, this Lagrange multiplier, times this 1, or let's call it x, times x. If x is 0, the entropy is 0 again. But if x is 1, then the entropy is contributed by the value of Lagrange multiplier at the saddle point. And that will give you finite entropy.
No, you mean you replace 1 by x?
Just replace this 1 by x or a small n, let's say small n. N can take the value 0 or positive 1 or -1. And then you can find that this at the saddle point of this evaluation, s is just equals to pi I lambda times n. And how to understand this chemical potential? The reason is the following. Usually when we're thinking about the BPS black hole in 3 dimensions, when we think about the BTZ, extremality equals to supersymmetry. But this is not true in general dimensions, because extremality usually means the horizon, outer horizon equals to inner horizon. Horizon depends on charges in very nonlinear way. So this is usually is not a linear relation between the charges. So, but the supersymmetry would require linear combination of the charges equals to energy. So these 2 conditions, supersymmetry and extremality generally are not the same condition for if the black hole contains the charges and angular momentum, etc. And so if you just impose supersymmetry, you can solve the sum of the data of the black hole. Let's say you might solve it to be like this one. Generically, some of the data will be complex, but it will be real if you require extremality, which means what the horizon takes some specific values. And this is the origin, turns out to be origin of this kind of nonlinear relations between the charges. So this is actually just, that's why we call it extremality condition. That really means the black hole is extremal. Otherwise, if you just impose supersymmetry condition on the black holes, you will just end up with the negative singularity. There's no horizon. Okay. And the BPS black hole, by I think by the people who are working on this topic, means supersymmetry plus extremality. When you see BPS, this kind of terminology for higher dimensional black holes, they usually means the 2 conditions are imposed simultaneously instead of just the 1. And so, and this complex nature or the linear combination of the chemical potentials equals to 1 is the conjugate version of the BPS condition. You can just take the black hole data, impose this condition, and then compute the corresponding chemical potentials. You will find that that's exactly just the 1 or -1, depends on your convention. But it will definitely, depends on your convention, that will definitely just be 1 or -1. It cannot be both. So which means generically for the black hole, we know, or for example, for the black hole, this picture shows, there's a specific value. We usually take the convention to be 1. That means usually when the index computation, sometimes like King other group thing, there exists another black hole solution. What does that mean? That means if you find the other black hole solution, you should find at least a linear combinatorial chemical potential to be -1. They think they need at least both of the black hole solution to exist to guarantee the unitarity of the superconformal index, superconformal field theory, which is used to count the black hole entropy. But the second black hole was never found so far. We only know 1, so we just play with this one.
Why is that related to the unitarity?
Because when you really compute the superconformal index, let's say for given rank SUN, they can just do numerical computation. Then you can see because of a -1 to the f, the fugacities might flip the sign, sometimes positive, sometimes negative, and it will for large terms it will be oscillating. For oscillating, then that means like there's a cosine, some kind of a function is controlling it. But if there's only some +1, then there's only exponential I something. Then you need another exponential -I something to restore the cosine. So they believe there is a just for this kind of computation, there is another black hole.
This is like extracting out the photonic part of the.
No, they are just computing the unrefined superconformal index. Unrefined means PQRS or whatever technical, whatever the fugacity, just take all of them to be equal. And so that's claiming the analogy. In 2D, what is happening is, there's some partition function. You use SL2Z modularity to approximate partition function, and then you do the inverse Lorentz transformation. That's a Cardi formula you have. But in 4D, Zafroni is telling us if you are smart enough to reproduce this formula to get the leading order of partition function to be of order n squared, then you do inverse Lorentz transformation, you can get an entropy of 1/16 BPS black hole. That's good. Then the work we did in 2018 or 2020 was trying to understand how to use this SL3 modularity to go from this step to here. And this is also most of the other works by King, Mercy, and Nini, and also Nianjun and the others. All of them are trying to use some kind of SL3 modularity to go from this step to this one. So let me just explain what is this SL3 modularity. So,
sorry, I still missed one small point.
Yeah.
So for previous slides, so why this right hand side equals to 1 is not the same, give the same constraint for supersymmetric Cosmanian? Why in the Cosmanian case you need it 0, not 1?
Supersymmetric Cosmanian energy has a specific definition that was first defined by Castani in 2014. What they did was trying to compute the partition function by localization on, let's say, S3 cross S1, and count all of the states and compute the partition function, and just by their computation of their procedure of doing this computation of the field theory defined on it, extract all of the states and compute the spectrum and the partition function. They call it supersymmetric Cosmic energy, and
yeah, that's right. Now we are talking about the constraint for the chemical potentials. So naively, supersymmetric Cosmic energy also need both the SUSY and the extremality.
Yes.
With 0 temperature quantity and the SUSY.
Wait. For extremality condition, I'm not sure what they mean. Actually.
On field theory?
On the field theory, I don't know what that. But imposing, imposing. Imposing SUSY condition is already imposing 0 temperature. I think in their model, and so So in that case, I think I checked before. They just give 0, but I think it's people's terminology to call this one with that the chemical potential equals to be generalized supersymmetric Casimir energy that to distinguish the one Cassani computed. So this is the superconformal index definition, or sometimes it's called the supersymmetric Casimir energy. So when you read the literature, it's a little bit confusing that something is called a supersymmetric partition function, something is called superconformal index. How are you going to distinguish them, or how are you going to relate them? I think my way of understanding it, let's say this is called partition function, everyone agree. And if I impose chemical potential equals to 1, linear combination of chemical potential equals to 1, I can eliminate phi 3 by replacing it by tau plus sigma plus 1 plus the minus 2 the others, and take it back to it, and you will get usually superconformal index. And that's why we usually, when we say superconformal index, supersymmetric partition function, we usually means that this one, together with the chemical potentials, linear combination to be 1.
Why do you need that constraint to define the index?
So this index, this constraint is consistent with supersymmetry. Actually, for example, if you just start from this supersymmetry, and let's say we are interested in black hole data. All of the black hole data are actually given from here. You can compute the corresponding charges and angular momentum. If you impose that condition, you solve all of the data and go back to check chemical potential linear combination. That equals to 1.
So that's 116
BPS. 160. Yes.
Okay.
So that's why I say it's a conjugate version of the BPS condition.
Thank you.
So, and that's a superconformal index.
Sorry, with your condition, do you also automatically get this minus 1 to the f?
Yes. So minus 1 to the f. So minus 1 to the f exactly come from. So when you replace this phi 3 by 1 plus something. So minus 1 to the f is exactly this 1 times this q3. So you should identify q3 with
F.
2f.
Because in this case, you're talking about particular Egan space, and then Q3 actually is somehow related to the
Yes,
to the,
yes.
to the spin.
Yes. And actually, that's consistent with all the letters of possibilities. And the integral form of the superconformal index is this one. And this part is a Haar measure. Haar measure is of SUN gauge group. And we want to evaluate at a large and generic. And these are the elliptic gamma functions. And there are 3 in the numerator, not just 3, x, I, j, and then. So you can forget this convention. You just say there are roughly 3 kinds of elliptic gamma functions in the numerator, which corresponds to n to the 4th degree of Mills contains 3 n equals 1 higher multiplets. And there is actually 2 gamma functions in the denominator, which corresponds to n equals 1 vector multiplets of n equals 4 super units. And what we are interested in is precisely what the properties of these elliptic gamma functions are, which are defined to be of this form. This might look unfamiliar to you, but what is more familiar to you might be the analog in the 2D CFT is this Q theta function defined to be here, where these tau sigma are just the chemical potentials related to these PQ fugacities by this exponentiation relation. And there are a few interesting properties of these elliptic gamma functions. This was first introduced in this paper in 1997. Some of the properties are here. And for example, this is one of the properties that the elliptic gamma function often use. And theta is just this Q theta function. And it turns out that this is the elliptic gamma function is a unique solution to this difference equation. And there are a lot of applications of this function. For example, this morning, Junya mentioned the 8-vertex model, and this elliptic gamma function is precisely the free energy part of this 8-vertex model. And hypergeometric solution of elliptic whatever difference equation. I don't know what is that. What is more interesting is it is a partition function of the nx1 chiral multiplets. And also, these kind of relations are very useful to show cyber duality by checking the partition function of the electric and magnetic theory are equal. That's what mentioned by Professor Shitman's talk this morning. And you can check this paper for the concrete computation. It's very beautiful computation just by using this form. But these are not just what we are interested in. What we are interested in is something analogous to modularity, which is this relation. So for q theta function, the modularity is when z becomes z over tau, and tau goes to minus 1 over tau, just like even just said in previous talk. And then there is a phase, which is the quadratic in z. If you just take z goes to 0, then you can just reproduce what you just saw for 2D CFT passing in energy. That's a tau plus 1 over tau term. And generally, how we usually do is in high temperature limit, we can set this one goes to 1, and then theta function is just approximated by this pure phase, and then that gives you a Casimir energy, and then you can reproduce black entropy. So this is a dominating one. And what is the property of elliptic gamma function is this one. So on the left side, there's only one elliptic gamma function. But on the right side, there are two different kinds of elliptic gamma functions. That's just because in the BPS limit, there are two different derivative letters in N2 superamines. So that the tau and the sigma just representing two different kinds of descendant letters of the superamines letters you are counting. So, but different from this one, this is no longer just a symmetry anymore. This is a symmetry because partition function just goes to itself up to a phase. But this is not symmetry because on the left side you have 1, and on the right side you have 2. That's not symmetry, right? And then there's a phase polynomial, which is a cubic in Z. This was found by Felder in 1999. And how to use that formula to reproduce entropy, and actually all of the work in starting from 2018 to understand black entropy is just doing the same thing. Take the cardinate, maybe not taking cardinate, but somehow they always have arguments to suppress these parts. And approximate elliptic gamma by this just a pure phase. And then take this back to this index, and then in the large n limit, they just reproduce this form. So this seems simple, right? Just as long as you know how to evaluate index, actually it's very simple because you're just replacing all of the elliptic gamma by a pure phase. So as long as you know asymptotic expansion, asymptotics of the elliptic gamma is this form, the story ends. But our work is trying to understand what is the origin of this modularity. And because it's no modular symmetry. Just like the 2D CFT SL2Z, you have is the geometric origin of the modularity is a flipping of the 2S1 circle. Then what is the origin of this modularity? Can we have any physical interpretation of this physical modularity? And another motivation is the Faraday. Because in ADS3 CFT2, you can take a tau goes to 0, that's the BTZ black hole high temperature phase. Tau goes to infinity, that's the thermal ADS phase. So there's a phase transition between them, that's a Hawking phase transition. And but except these two, there are other saddle points in the partial integral, which means that when tau goes to any rational numbers, and this partition function will always have some kind of Euclidean complex saddle contributing to the partition function. And actually understanding these saddles together with some non-saddle contributions is very important to understand the information paradox. So can we do that also in the 4D SCFT? So this is all related to the modular structures of this elliptic gamma function. So that's the main topic I want to explain today. So let's say something geometry. The geometric ground is, let's say some topology is consider three-dimensional manifold which have this kind of topological operation that you have two solid torus. Solid torus means it is not just torus, it's a field with everything. It's solid. And then kind of operation is called Higa splitting, that any three-dimensional manifold can be split into genus N manifold of this kind. So the example I'm giving is genus 1, okay? And these are just two solid torus. And topology is D2 cross S1. So this part is D2, S1 is here. And this operation is gluing a 1, 0 circle with 0, 1 circle. So this is S transformation gluing two solid D2 cross S1 manifold. And this usually is called genus 1 because splitting I denoted it in this way. HG is just a handle body of the genus G. And in our case, in our talk today, we're only interested in G equals 1. And F is some kind of gluing elements which to generate the three-dimensional manifold. In this specific case, F equals to the S generator, which is this one. So because we are gluing along the boundary, and the boundary there are some diffeomorphism, and so there are some redundancies of it, and these redundancies are defined by the so-called mapping class group. And some of the example is if you use identity elements to glue two solid tori, you just got S2 cross S1. If you use the S generator to glue two solid tori, you got an S3. And you can just think of, for example, this kind of gluing as there is the interval, and there's the two S1 circle vibration over it. And generically, for more generic, it just means it's not just the S generator, but instead of any SL2Z generator to glue the geometry, we will get a so-called length geometry, LP, Q. PQ automatically to be coprime, and so this is because this is the SL2Z elements. O is the orientation reversing, so this is the diagonal 1 minus 1. This is the group element I used to glue two solid torus together. And this will realize the length geometry as the gluing of the two solid tori by this kind of glue elements. This is one definition of length geometry. Alternative definition is if consider some kind of S3 coordinates, and then you do a further or secondary quotient which relate to P and Q data. In this way, PQ are coprime, and then this will be also as length geometry. But you can see these two definitions are not fully equivalent. There are some redundancies in using group elements to generate the new manifolds. So these redundancies are described by, for example, this gamma infinity group elements, which means if you have a non-contractile cycle and a contractile cycle, and if you glue the non-contractile, do a linear combination of the non-contractile cycle with the contractile cycle, it is still non-contractile. So this will not change the topology. It's still the same length geometry. And actually, there are a lot of these kind of redundancies to describe the length geometry. For given a P, for different Q, they have the same homotopy group to be ZP. But for it's not all of the Q, they have the same, they are the same manifold. It is Reidemeister in 1935 realized although they have the same homotopy group, but homotopy group acts on the manifold in different way for different Q. So the equivalent length geometry are subject to either of these conditions are satisfied. And they actually come up with a very good geometrical quantity called the Reidemeister torsion to distinguish different or inequivalent length geometry. If Reidemeister torsion gives a different answer, then they are different length geometry. for example, L7 comma 1 and L7 comma 2 are different, but L7 comma 1 and L7 comma 3 are the same. This is a very non-trivial thing to check. We are interested in 4 dimensions. So in 4 dimensions, we just need the extra S1. So S1 cross S1 is T2. So we will glue 2, 3 solid torides. And then you got 3 S1, S1 from the boundary of T2 and the 2 S1 from here. That's the origin of our SL3Z modularity, because we are trying to swapping the 3 S1 circles. And then you can use any group element to gluing it in this SL3Z matrix. For example, S23 will just give you the corresponding S3 cross S1. If you use identity, you will just got S2 cross T2. That's just a generic gaming, topological game you can play with. But just like I said, there are some redundancies also. Like there are redundancies in the definition of the 3D length space, then there are redundancies in the 4D length topology. So when you are studying this 4D length topology, and the ambiguity is more than just the gamma infinity, is actually you have the 2Z2 redundancies here, and there's SL2Z redundancy. SL2Z redundancy comes from you have 2 non-controllable cycles, so you can always do linear combination of them. And the 2Z2 corresponds to there is linear combination of one non-controllable cycle, 1 controllable cycle. So that's the origin of it. So if 2 gluing elements are related to the H is the elements in this group, then they are always generating the same length geometry, because this is just a diffeomorphism. And then for the crucial point is in SL3Z, there always exists H and H tilde such that you can write the general SL3Z elements in this way. So that means for all of the gluing elements in SL3Z to generate 4-dimensional manifolds, that's always some kind of length geometry up to this ambiguity H and H tilde. So we will write this one or the gluing manifold in this way. So D2 cross T2, D2 cross T2, and the rho tilde are just modularized in these 2 solid tori, and there is a gluing element to generate it. And we will further use, if we consider this ambiguity generated by H and H tilde, and then we will just use H and H tilde to glue the manifold, and these 2 are just describing ambiguity in the gluing solid tori. And our point is just trying to argue that if so this is just a geometry, and if we try to study supersymmetric theory defines on it, then there will be consequences. That's what that's our main topic today.
So rho again is
Rho is the 3 moduli 1 sigma tau.
oh, okay.
Thanks. So let me first mention a physical. So I just finished some geometric foundation. So let's talk about physics. That will be much easier. So in 2015, people figure out that in the 4-dimensional superconformal index have some kind of a factorization structure. That means, for example, let's just call the supersymmetrical partition function could be length index, depends on P comma Q. Generically, it can be factorized in terms of 2 different holomorphic blocks, and the first one is the defines holomorphic block, the second one is just there is a group elements that acting on this corresponding moduli, and the summation is over all of the Higgs vacuum, and there's a universal phase that does not depend on the state, which is described by this alpha Higgs vacuum. Then if you define and consider any chiral multiplet, let's just focus on n=1 chiral multiplet, define some D2 cross T2, the one of the solid tori, the localization is telling you this result just resulting in a single illegal gamma function. There are a lot of paper in that. And there's another name for it, just the holomorphic block. And this structure is called holomorphic factorization in 4 dimensions. This is, according to us, or according to the intuition by God, this is reflecting some kind of Hilbert splitting. That means there is a holomorphic block here defining some partition function of D2 cross T2, and this is another D2 cross T2 partition function, and this is the gluing manifold partition function. And similarly, on S3 cross S1, the partition function can be also computed by localization method, which is shown to be gamma z top sigma. And then this gives us very good explanation of what is the meaning of this modularity for elite gamma functions, or geometric meaning of it. This is equivalent to say if the partition function of S3 cross S1 is precisely just the product of 2 holomorphic blocks, and each of the holomorphic blocks are partition functions of B2 cross T2. And the corresponding holomorphic block is chosen to be determined by this S generator, because this is not z tau sigma but z over sigma. So this is S13 generator acting on the moduli. There are a lot of these kind of identities of the illegal gamma function. For example, this is also identities of illegal gamma function. But 1 over theta is the partition function of S2 cross T2. And these two are holomorphic blocks of S2 cross D2 cross S2. So this one is telling you S2 cross T2 is glued by D2 cross 2 copies of D2 and the T2 by the identity operator. This is exactly telling you that. So you can find a lot of these kind of identities can be interpreted in terms of this geometric operation. And especially when these two gluing elements are related in this way, they should result in the same partition function. And so, which means, what is the special thing about this S13 generator to be used to define the holomorphic block? There's nothing special about it. Actually, any group element in SL3Z can be used to define the corresponding holomorphic block. So that's just exactly our motivation. So basically, this is due to the fact that the partition function generated on the corresponding manifold. The manifold is defined by gluing 2 solid tori, but the 2 solid tori contains some boundary condition on its boundary. We are gluing its boundary, so the final physical theory on the partition function, on the manifold we are gluing should not depend on this boundary condition. And in NX1 theory, there are 2 different boundary conditions.
So there is this information about choice of vacuum, right?
Mm-hmm.
Choice of vacuum. That is that Kaiser? Yeah.
Right.
Right.
Because we are just playing with NX1 chiral multiplet. So.
And what does it mean by I of Kaiser? What? Left side.
That's the index. So let's say this is 1 comma.
Choice of vacuum.
We're in the same state because we are just playing with a single n=1 chiral model. You can just forget alpha in this model. But if we are playing with something more complicated, address corpus or SQED, then you need to sum over.
Thank you.
But because in n=1 theory, there are 2 different boundary conditions you can define. One is Dirichlet, the other one is Robin. And they are related. You can expect that they are related by some boundary data, and the boundary is 2D, so that's some kind of a 2D partition function. And you remember, like I said, for illegal gamma function is a unique solution to this equation. So this actually can be interpreted as 2 different kinds of blocks. related by actually originated from different boundary condition, and this Z partial is exactly a 2D partition function. And in terms of modularity you just saw, there are two different kinds of this kind of modularity. One is what you just saw. The other one is this one, which is also true, but their phases are different. And this is just this is the Dirichlet boundary condition. This is Robin boundary condition holomorphic blocks. But they are also giving the same index on the left hand side for S3 cross S1. Then just this, I still have 10 minutes, right? Or
Yes, 10 minutes.
10 minutes?
Yeah.
Okay, good. I think I can finish. Just for different boundary conditions, generically, I can write down the index should be written in terms of this form. For different boundary conditions, so index should not depend on this boundary condition, so the index should be equal. And then that will impose very non-trivial constraints at the factorization level. That's what we mean by modular factorization. At the factorization level, this is very non-trivial. So you can impose you can ask whatever is H and HQ are allowed, and then that's actually this solution you can find for generically lens geometry LP, Q. And the P information of a lens geometry appears here. So that means that this ambiguity defined by this H, this M parameter should be co-prime with some kind of P here. P combination here. So that's some kind of, the ambiguity is not the full SL2Z cross Z2, but there are some compatible subgroup of the transformation can act on the lens geometry. And let me skip this one. Let me just give you one example. The most general S3 cross S1 factorization formula, which means that a single elite gamma function can be factorized into two, but we have M and N tilde now, and M and N. And it seems that if you look at this formula, and this is valid for all of M and N coprime, M and N tilde of coprime, and then there's a single phase. And this phase is just a single Q, still the same Q polynomial with 1 over N prefactor, and a constant called the generalized Ledinkin sum that was also appearing in the theta function. If you consider some kind of a general SL2Z transformation, there is some kind of a Ledinkin constant, a Ledinkin sum constant here. And what's interesting is this will exactly give you, if you tau and sigma approaching to some rational number, these two will goes to 1, and you can approximate the gamma at the tau and sigma goes to some rational number by pure phase. And the pure phase is expressed by 1 over N, and then that will give you finally indication the entropy of the corresponding complex Euclidean saddle entropy will suppressed by 1 over N. So that's an indication of some generalization of the fairy tale story in 2D. And actually, that's also some Samuel Murphy what they did in 2019 similarly. But I want to provide this wonderful example to you because this is one of my favorite results from this work. Is by this factorization method, we can actually study lens geometry for LP, Q, because before our work, there are almost no work that can study general Q, or all of them can only study Q equals to 1. But by using factorization method, we can compute the corresponding base polynomial for LP, Q. So generally P, Q, P and Q are co-prime, so you can use Euclidean algorithm to find the continual fraction expansion of the P over Q. And there will be, let's say, it takes T steps to realize it. And then there are a lot of intermediate steps if I is smaller than T. So these are usually called convergence. Let's call them just a convergent matrices. And this data appearing in the, you apply Euclidean algorithm to generate, to find the greatest common divisor of two coprime number. There are a lot of data between them. And they can be used to exactly compute what is the length geometry partition function. And there are t+1 number of elliptic gamma function there. And by using the corresponding factorization formula, because you can use some kind of properties of gamma to put one in the numerator, put this one to the denominator, you can replace each of these gamma in terms of this form. And if you tune those data inside this M and N data very carefully, you can figure out there is a cancellation that this one can cancel that one, this one can cancel that one, and eventually it will result in only two gamma function left. That's precisely some kind of factorization structure of the length geometry or length geometry partition function. And you can compute its corresponding phase. So the corresponding phase structure is very interesting. Except a single Q polynomial, there's something extra term, and the extra term depends on Dedekind sum of the P comma Q, or P comma S. S is QS minus PR equals 1. So, but they define the same Dedekind sum. And what is the Dedekind sum to the length geometry was proposed by this paper. I don't know what that is. This terminology is called. This is some mathematical paper, so so I don't know. But I want to emphasize its consequence on the anomaly polynomial. You can see, compared to the if you look at into the literature, all of the maybe all of the literature give you this S3 anomaly polynomial. But if you see what is the contribution to the P comma Q anomaly polynomial, it seems all of them are just reflected in this FGG term. G is a graviton, F is the flavor, R is R charge. It's all here. And this result was given by Neely and Pascali, but our factorization method can help us compute general LP comma Q, which deformed this FGG term to this one. And this seems to be only term that is sensitive to this Q information. And this P comma Q is this one, zeta, eta T is the Dedekind sum I just showed you. And to summarize, just one more thing, that the partition function in 4D you can prove to satisfy this formula because it depends on group elements. And we actually proved that by our factorization method in our paper. And the mathematical structure of it is called, it is automorphic form of degree 1. And what you are more familiar with is the 2D partition function satisfies some invariance relation. That's automorphic form of degree 0. And let me skip this one. And just our guess for other dimensions is just summarized in this table. What you are more familiar with the 2D SL2C modular group, and its automorphic form is just some kind of genus, and elliptic genus, and its geometric origin is just a swapping of the 2S1 circle. And what we are studying in this paper is in 4 dimensions, the modular group is SL3Z, and the automorphic form is of this. Automorphic form is of degree 1, and it is an elliptic gamma function, and the geometric origin is the Hilbert splitting. But you can fill in the rest of the table in other dimensions that's some kind of proposal and guessing. And Gukov had a paper roughly proposing 5D or 6D, and there's some kind of a transaction operation on the topology side. There are 3 parts of the partition function. So in the end, let me just summarize our work. Our work is trying to prove there is some kind of modular factorization structure in 4-dimensional partition function, and that's related to ambiguity of the Hilbert splitting. And we use this kind of proposal to work out the length index partition function and its factorization and the corresponding anomaly polynomial for future directions, including whether you can do the modular bootstrap for this kind of SL3Z modularity or not. And fairy tale story, or one more interesting thing is whether, because we are computing the length indices, so can you figure out any gravitational dual to this length indices for example, any ADS solution of the ADS black length, I don't know, and maybe study Schur limit. My colleagues say Schur limit of this factorization formula will lead to the quantum modular forms, but you can also refer to Evan's talk in the Yanni's paper for other related topics.
Thank you.
1 minute?
Sorry?
No. Questions?
So for the factorization, I saw many slides you show the factorization for the integram, not for the integral.
Right. So because we are studying the in this work, we are trying to show that by in this n=1 chiral modulus. That's just a single gamma. If we want to say integral, the whole integral, let's say consider n⁴ super Yang-Mills, then you need to replace each of a single gamma by this formula and take that into the integration over Haar measure and take all of the residue. And then it will also be factorized the formula, but the sum of all of the states, and the states are exactly the residue.
Is that a finite sum?
Depends on the theory, of course. I think for SQED it is a finite sum. n=1 SQED is a finite sum.
So for the n equal to 4.
For the n=4, it's not. I think it's not.
Okay, so you just keep rid of this leading term easily minus.
Yeah, and because you have the infinite contribution of the vortex parts, right? How many vortex?
Yeah, that's true.
So what is the meaning of the phase? You show the modularity is not a modular environment like Egan. So what is the meaning of the phase? The relation to our phase.
Okay. So I can just refer to list one. So the phase can be decomposed into a coefficient of this term, for example. For example, it contains the R cubic anomaly term, and it contains the R graviton graviton term, and it contains the flavor graviton graviton term. When you just take the two polynomial, you can match it to this one, and each of the term can find its position here.
But then these are related to A and C. It's very clear.
It's for A and C. You mean for specific theory like n=4 super Yang-Mills, or
No, in general, n=1.
for a general n=1, I think you are okay, very good. So for general n=1, Kasani's paper, he actually computed this anomaly polynomial related to this supersymmetric Casimir. A is the trace over R cubic minus something, 1/24 or something, and there's a number which is which means you can extract this number from this one to extract the A and C value.
You don't remember the result.
I don't remember the result.
Does it make sense to perform an SL3Z operation on the entire index and get something on the right?
Sorry, SL3Z index on the guess.
You have the index and you perform SL3Z on the index. Before the operation, you have a factorization.
Yes.
After the operation.
I can say there is such application we considered before, but I don't have any good intuition for that. But for example, let's see this one. If I do a specific SL3Z action on this one, I can change this one to be Z of sigma. the ordinary elliptic gamma. And then I can take tau and sigma goes to two different free rational numbers. So that will give us the fairy tale for gamma and sigma take any two independent rational numbers. So we need this kind of the SL3Z action on a length index, as you said, to generate the complete fairy tale story. But for the geometric meaning of that, we're not sure.
So what is this modularity in black hole?
So the modularity in black hole.
Yeah, we were talking about, let's say you take an input 4, you would perform this as a.
So we do not know this one because this is the length geometry. So that's why I propose in the end, if there's someone can figure out the black length, then we can say that. So let's just say this one is more relevant for black hole, and the tau and sigma goes in. I think in the question you are asking is for specific transformation, S transformation, acting on the elliptic gamma function, that will be a black hole. For some other transformation acting on it will be other saddles. It seems that it's just a full partition function. These saddles are related. Black hole saddles related to some other saddles by this kind of SL3Z kinds of the transformation. But on the gravitational side, there is something called the gravitational block. But whether that block is same as a holomorphic block, I don't think that people achieve the conclusion.
Does it come from localization calculation on ADS or something? Those gravitational blocks, what are they? How did they find those?
I forgot. Sorry. It is Hossein paper, I think.
Okay, thank you.
I can send you later.
Any other questions?
Can we understand the factorization of length space as according to the fixed point of U1 action? For example, if we consider the sphere, we have fixed point, we can consider North Pole and South Pole with fixed point of U1 action of rotating the sphere, and then according to two fixed points, we cut into two North Hemisphere and South Hemisphere, and then we have North Pole, South Pole appears at each hemisphere. So I wonder if we can understand factorization for length space in a similar way.
For example, I think this one is like identity gluing. For example, let's say S2 is easy to imagine. S2 can be split into D2 and D2,
Right.
Gluing along the boundary. One is related to North Pole, the other is related to South Pole. They are just glued by identity operator.
Yeah.
So identity operator.
Length space is
So length space is generically glued by SL2. For example, in 3D, that's glued by three-dimensional length geometry is glued by SL2Z elements. But if I just say S2 cross S1 and split into D2 cross S1 and one North Pole, South Pole, that's just glued by a single identity element. That's a special case of this gluing procedure.
Any other questions? So if not, let's thank the speaker. So we will resume 5 minutes or something, so just take a quick like.
What I was about this is supersymmetric, yes. If not supersymmetric, that Oh, so for other OEM, so I think there are two ways of operating supersymmetric. One is whether the manifold if the cost is S5 or other but the AS time is always this. So that doesn't make a difference. But I think you
Maybe you can answer these questions first.
Okay.
I'll take care of I don't know